Good afternoon. I'm Jaime Garcia Jr. I am a junior at UTRGV, majoring in mechanical engineering, hoping to specialize in material science. And this is my midterm OREU update. My mentors are Dr. Brady Butler, Nicole Person, and Daniel Lewis. I'm a researcher for the aerial lab, helping with the simulation and design. And this work was supported by Los Alamos National Laboratory. The focus of the aerial team is to advance in-house testing and research for metals in a hypersonic environment. Hypersonic aircraft are aircrafts that fly at speeds of Mach 5, which is approximately 1,715 meters per second, or higher. And at these speeds, the aircraft will reach temperatures of easily over 1,500 degrees Celsius in the leading edges. Most of the heat is in the leading edges of the aircraft. As you can see here in the Concorde at Mach 2, the nose and the leading edges have the highest heat. However, it is good to keep in mind this is at Mach 2. At Mach 5, and at heights closer to the surface, the temperatures will easily reach much higher. To study the effects of a metal in a hypersonic environment, a mini tensile test machine capable of recording accurate mechanical properties of metal at 1500 degrees Celsius is being developed by the aerial team as we speak. The materials to make and test the mini tensile tester are expensive, however. So, to lower the cost and save time, modeling and simulations will be conducted to gain an accurate behavior of the mini tensile tester under various loads and temperature. This is the mini tensile tester, and I will be focusing on the grips, as we can see here in the ARL MT1. Autodesk Fusion 360 is the software that we'll be using, and it also allows for CAD, computer-aided design, and simulations. It visualizes von Mises stresses and simulations. The von Mises stress helps predict the stress an object can handle by quantitatively showing numerous stress states for a singular point in an object. The focus for the modeling and simulation are the tensile test grippers, and the goal is to optimize their stress dispersal. Simulations can show the deformation an object will experience when subjected to loads. This is good because we can break these virtual grips before we subject the real grips to stress. And we can see here that the von Mises stress for a singular point, this is just for 6 different states. The good thing about the CAD is that we can do every single point throughout the entire model, and this helps visualize where the stresses are the highest. As we can see here, where the sharp edges are at, the von Mises stress is at its highest, around 0.0251 megapascals and greater. Here, the maximum deformation of the grip at 5% of the model's entire size is shown. This helps us visualize where the weakest points are within the model to help better design future iterations. The current ARL MT1 sample has the highest von Mises stress around the corners sections of the grip, the sharp corner sections of the grip. To lower the stresses in this area, the largest fillet will be applied to smoothen the inner grip section. The filleting tool allows for 2 corners to combine into around the edge. The larger the fillet, the larger the arc around the edges, and the largest fillet on the inner grip curve allows for a lower von Mises stress, implying better stress dispersal. Here we can see we applied the largest fillet, and it is much darker blue in color, which indicates a much lower von Mises stress. Potential designs will be modeled and simulated to see where improvements can occur. Mesh optimization allows for the accuracy of the simulation due to a finer shape constraining the model, but requires more processing power and time. ANSYS will be used for its complex finite element analysis and to better simulate the thermal properties of the grips at 1500 degrees Celsius. Unfortunately, we do not have an infinite budget, so research into material properties will also be done to find the best material for a 1500 degrees Celsius environment with our given budget. Here we can see a potential design, and here we have 2 different shapes, one with very coarse mesh sizing and one with very fine. The very fine one covers the detail much more accurately, so the simulation is much more accurate. And here we have different metals and materials used for various hypersonic ships. The SR-71 has titanium, the X-15 has Inconel, the Orbiter uses ceramic tiles and blankets, and this airplane up here uses ceramic matrix composites, or CMCs. Acknowledgements. This work was supported by Los Alamos National Laboratory. I would like to thank Los Alamos National Laboratory for the funding and the ARL team for their feedback and help throughout this entire internship. These are my sources cited, and thank you for your time and listening. I hope you guys have a great one. Bye.